Hi Wildcats, this is the Unit 4 focus question for overview video where we will be looking at magnets. Um, in particular, we'll look at how magnets behave and what their characteristics are and some of the ways that we use to describe magnets and forces and fields around them. Magnets are fun. We've all kind of maybe played with magnets at some point, either in school or just refrigerator magnets. And so there's some things that maybe we recall. First, all magnets have two poles, a north and a south pole, they're termed, and they can actually never be separated. Magnets are what we call these dipoles because there's two, di meaning two, so dipoles, two poles, a north and a south pole, and it's impossible to separate them. Scientists have never found a monopole or one pole where we would just find north by itself and south by itself. So if you want to become rich and famous, discover a magnetic monopole. Um, we can test that if we took a magnet and chopped it in half. We wouldn't have a north and a south pole. You'd have two smaller magnets, each with their own north and south pole. And if we took these and chopped them in half, we would have smaller ones, and on and on and on. And that actually is going to help us in a later future focus question kind of understand uh, why magnets behave the way that they do, all the way down at the atomic structure. Because you could take this and just say, keep cutting these in half until you got all the way down to an atom, right? Then what? We'll look at that later. Some things you maybe know if you've played with magnets before is that if I have two like poles, like down here, two north poles, and I try to push them towards each other, they push against, so they repel each other. And if I have a north and a south pole, they are attracted to each other. So just like when we did electric charges, opposites attract and like repels. Um, because we notice that there's an attraction and a repulsion, we call that like they push or they pull towards each other. And so that push or pull is what our definition is of a force. And so therefore magnets must have a force, and guess what? It's called magnetic force. Any magnetic objects can exert magnetic force on other magnetic objects. And so just like before, the symbol for all forces is F, and then we use these subscripts to denote the difference between them. So electric force was F sub B, this is F, or excuse me, F sub E, this is F sub B. It's not M for magnets, it's B for magnets, because it is. Just like all other forces, the unit for them is newtons. Okay, so how the heck do we determine what's the north and the south pole? Well, really, are kind of arbitrary, and it's just the system that we use. A good way to do it though is the north end of a magnet will always point to the north direction, north on Earth. And so then the other one must be the South Pole. I wish there were a better explanation for that, but that's just kind of how we determine that system is the north pole of a magnet, so a bar magnet that I'm holding in my hand, the end that points north towards the Earth. The north pole of the Earth is the North Pole. It's as simple as that. Okay. Um, we saw before that electrically charged objects have fields around them, and it's those electric fields that produce the electric force. The unit for that was newtons per coulomb, and we use the symbol E. Guess what? Just like electric charges, magnetic charges, or excuse me, magnets have fields around them. They are non-contact forces, so they act without touching, and so it must be a field force, and so therefore there must be a magnetic field. Again, the symbol for magnetic field is capital B, and the unit for it is Tesla, not the car, but Nikola Tesla, who was a famous scientist from long before you were born. Um, Not that you need to know this, but I just thought it was interesting that a Tesla is equal to a Weber per square meter. And then I guess it's also equal to a Newton per amps times meters. But this Newton guy I've never heard of. This Weber guy I hear is kind of famous. Okay, so because there is a non-contact force or a field force like magnetic force, it is caused by a magnetic field. And so we need to be able to represent that magnetic field. Where you'll notice, so here's my magnet, we've got field lines drawn, and this looks a lot like the electric fields that we just covered, except it's not positive and negative charges now, it's north and south. And so we use those same systems where we use arrows left or right to indicate the field. But something I wanted to point out that we didn't look at in electric fields is magnetic fields are three-dimensional. So here is a bar magnet. This block of like acrylic has magnetic, like iron pieces in it, and so they're attracted to the magnet. So if you drop a magnet in there, you'll see it's not as simple as just left and right across the page. Magnetic fields are in 3 dimensions. And so uh, if you were ever in a situation where you needed to draw a system going out of the page or coming into the page, we would use X to go into the page and a dot to represent coming out of the page. So a good analogy for this is, if you think about it, if you shot an arrow going away from you, you'd see an X where the like fins are traveling away from you, and if an arrow was flying towards you, one, you should duck. Two, you will just see this dot coming at you. So that's kind of how I remember it. Most of the time we're going to deal with in plane field lines, but it's worth noting and understanding that these fields, magnetic fields, are in 3 dimensions like we see here. Okay, so what are the rules for magnetic fields? Well, magnetic fields always go from the North Pole to the South Pole. So you can see that the direction of these arrows here, all the arrows leave the North Pole and travel to the South Pole. And because we always have dipoles, so a North and South Pole together, those arrows will always go out of the north and then travel in a continuous loop until we get to the South Pole. So we have to create closed loops here, or they have to go off to infinity. So in reality, this line is continuing. So this line right here, you can see, but it's going to run off the page if we continue it, right? So like, and then it would go here, on, and then eventually, poorly drawn, but it would loop back here. Or eventually we run out of paper, so we would draw them going off into infinity, and that's fine too. But if they are able to be drawn, we would connect them back to the South Pole. Just like electric field lines, these lines never cross, and just like electric field lines, the more of them there are, the stronger the magnetic field, and that is called magnetic flux. It's just worth knowing that that's the term for it, and we won't necessarily use this symbol. Also, Tesla's is the unit for magnetic flux, or you can use this much handier one, the Weber. I'm just kidding, it's Tesla's, but you could also use Weber. And so in this picture here, where we're kind of zoomed in on the North Pole, you can see there are lots of lines leaving the North Pole of this magnet right here, right at the pole. And so this would have a high magnetic flux or be a stronger magnetic field right here. Here we see 2 lines passing through this circle, and so this would be medium. And as we move further out, we end up with just 1, so this would have less magnetic flux, or the field would be weaker here. Okay, and so that's the same thing we see here. The poles, as we look at these pictures, or this one's probably a good picture, since these are actual iron filings around an actual magnet, and you can see there are tons of them stuck to the poles. Well, why? That's because as we approach the poles, we are encountering more and more magnetic field lines, and so the field must be stronger here. And as we get out here, there are fewer fields, and so, or the field lines are fewer, as drawn, and so that's representing that the magnetic field is weaker out here. Okay, so in general, the more field lines we're drawing, the more magnetic force there is, and that's why we see more iron filings attracted to the magnet. Okay, so those are the rules for drawing magnetic field lines. Magnets can interact, right? So here's just our magnet off by itself, but if we took 2 magnets near each other, a north and south pole, we would draw, right? The lines always come out of the north and they always go into south. So this would be an example of, we would just draw straight across. So these magnetic field lines are going from north to south. So if we dropped a bunch of iron filings all over the place, we would expect to see most of them in this region right here. Like poles repel, so we need to come out of the north, but these field lines can't cross. So we would see this pattern right here, and if we took a bunch of iron filings and dropped them, we would see a ton of them here and a ton of them here, because there's a ton of magnetic field lines in that location. But we actually would see an area where there was no iron filings collecting, and that's because there is no magnetic field here. Those magnetic fields are repelling or kind of pushing off of each other, and so we end up with an area where no iron filings would collect because there's really no magnetic field there. And that's something that we'll be able to observe in class when we do some labs coming up. Okay, so those are the basic characteristics of magnets and how they behave in their fields. I think this is always worth talking about because we live on Earth and this is something we might experience. If you've ever held a magnet, looked in a magnet, you know that there's a needle, right, that has a north and a south pole. So that must mean it's a little magnet. When you hold it there, the north pole or the red end always points north. That's the red side of it. So if the north side of my magnet always points north, what does that tell us about how the Earth behaves? First, it tells us the Earth must be acting like a magnet. So that's one thing that maybe we don't always think about is the Earth itself is actually a magnet. But what does that actually mean about it? So if we did this, right, so here's my compass. I just have a little compass needle and the compass. This is north, so I should draw it in red. So here's the north side of my compass, and this is north, and then this must be the other side. So this is south. So the north end of this magnet is pointing north, and we just talked about how opposites attract and like repels. So the Earth is acting like a magnet. We could draw field lines that go oops, like this around the Earth, more of them, right? We say these are called the poles. Well, why are these called the North and South poles? Because Earth is acting like a magnet. But if we stop and think about this and pretend that for a moment the Earth is itself a magnet, the north end of my little magnet in my compass would not be attracted to the North Pole of the Earth, would it? It would be repelled actually. And so in reality, this pole is the South Pole of Earth. It is the magnetic South Pole. I know. That's opposite of everything you've been told. And so it turns out there's two ways to describe Earth's poles. The first that we use every day is the geographic north. So geographic north, this is where Santa lives, right? If you're into that sort of thing. And so we call this the North Pole, and geographically it is the North Pole, but magnetically this is the South Pole. It has to be because any compass that I hold in my hand, the north end of that needle points up or towards, not up, but towards the geographic North Pole, and opposites attract. So if this is the north side of my compass, it has to be attracted to the South Pole of the Earth. So therefore, the North Pole, the geographic North Pole, must be the magnetic South Pole, and therefore this means that this must be the magnetic North, but we call it the South Pole. That's where penguins live. But it is only the geographic South Pole, not the magnetic South Pole. So I think I have, yep, another picture here. So, right, this is something on the right side of this picture that you would accept, right? Here's the South Pole of a magnet. So clearly, if I took a compass, the red or north end of the needle would point towards it. We say that exact same thing on Earth. So therefore, this is what it must look like. We have visualized the actual magnetic field lines around Earth, and this is a visual representation of them. Like the magnetic field lines around Earth is a magnetic field, and we'll talk about it coming up, but it is that magnetic field around Earth that protects us and in large allows life on Earth to actually exist. So kind of an introduction to magnets and an application of them. They literally keep us alive, and everything you've been told about North and South poles is kind of sort of a lie. So I hope that helps, and we can go over questions that you have in class.